Do you follow me? So I can rewrite it this way. Oh, it is n factorial divided by k plus 1 factorial, and then n minus k plus 1 factorial, and then this k plus 1 can be multiplied in front, and I convert it. Then take a look. Can you use choose notation to represent this thing? If you use choose notation, what is it? If you use choose notation, it is n choose k plus 1 by definition. So I found the relation like this. Then by applying this, we can finish the proof. By applying this to the top line, we can finish the proof. So let's finish it unless you have questions. I will pause so that you can completely follow the second step, second crucial step. But this step isn't very bad. It's the straightforward calculation with the definition of the choose notation. Then with this thing, what can you do? For instance, assume that we have this case, n. So I will finish it. So example, assume that you have n multiplied by n minus 1, choose. What number do you like? Pick any number. Pick some number. For instance, 0. Assume that you have this case. Then, because of this relation, k equals 0 is applied here. So what is the conclusion? So do not focus on the intermediate steps, only focus on the relation. This thing can be written in this way. So if you use k equals 0, right? If you use the fact that k equals 0, then what conclusion can you get? It is what? 0 plus 1, that is 1, right? Multiply by and choose 1. So it is essentially and choose 1. Do you follow me or not? So we can vary k. So k equals 0 is handled. Then what about other values? So let's do it step by step. If you cannot grab the idea of a generic term, always use one term at a time. So I use the 0, then the next term is 1. And the next term is 2, and so on. So I will do 1. Then it is k equals 1, right? So 1 plus 1. And then and choose 2, or 2 times and choose 2. So we can continue, right? We can continue these things. And choose n minus 1, choose 2 equals, because of this fact, k equals 2, so 2 plus 1, then, and choose 2 plus 1, 3, right? Then it is 3 multiplied by, and choose 2. So do you need more terms, or you can handle generic term? After doing a few concrete cases, you may jump to a generic term, or you can continue. Do you want me to continue? Sorry, thank you. So do you want to jump to the generic term, or do you need more of this sort? So let's go to generic case. So assume that we have, for instance, k minus 1, generic one. Then and choose n minus 1, k minus 1 equals k minus 1, replace this thing, then k minus 1 plus 1 is k, and then k minus 1 replace, and k. So as you can see, we have this back, k plus 1, the same number, right? The same number and the same number. So we can write all the way through. And what is the final term? Let's go back and then find the final. Final term is when k equals n minus 1, right? Final term is when k is n minus 1. So if we have m minus 1 here, if you have n minus 1 here, I'm sorry, this term does not, just k position. So n minus 1, and then here, this is called k, right? So k happen to be n minus 1. Then it is by this thing, n minus 1 plus 1, right? And then n choose n minus 1 plus 1. Or it is equal to n, and then n choose n, matching number, right? We have the matching number. We have the matching number. So we can completely rewrite the above expression using what? Using what? Take a look. 1 times n choose 1, 2 times n choose 2, 3 times n choose 3, k times n choose k, or n times n choose n. We can completely rewrite the terms. So I will go up and then show you the result side by side. Take a look. I will write it underneath. This way you can compare it. So by the fact, this can be rewritten, right? This is what? 1 times n choose 1. I already showed you. And then this is what? N times right? And you can write these things. And then n times n choose n. So if we calculate this thing, then it is n multiplied by 2 to the power of n minus 1. I completely proved it. So I will pause and you can check whether you completely follow or not. So the first step is nothing but the binomial theorem application. Second step is a little bit of calculation, converting n times something into this kind of pattern. Then I will mention about I overview the chapter 2 and then mention about some early development and then go to 2.2, which is the core section of this course. But if you want to stop me, then stop me and question. No questions? So chapter 2 is the real beginning of the theories. Chapter 1 showed you some method of proofs, and those things can be covered in other courses too, not just number theory. But chapter 2 is the beginning of real number theory. So, the important thing is divisibility. And in number theory, significant part is about integers. So in some sense, 99% might be integer theory, right? There are many different types of numbers, but significantly, we focus on integers. Then, we assume that we have two integers, like 101 and then 111. Then can one divide the other or not? In this case, this does not divide the other, or vice versa. So we want to check the relation between integers. So we want to define the divisibility. And then want to develop some powerful theorems that can be applied in high tech. So essentially, what you handle is not very difficult. But because we provide proofs, eventually, if we stack these easy things, then it will become high-tech. This stack will become a high-tech. So one step at a time we should follow. But before going any further, earlier, what kind of things? What kind of things were considered by people? Early number theory. People consider these kind of numbers, as I showed you before, the number like this, or a number like this, and a number like this, and people easily figure out how we can represent the generic term, right? So it is 1, and then this is nothing but 2 squared, and this is nothing but 3 squared. So these are too trivial. So no big challenge, right? Then people or triangular numbers, right? So I covered these things already, and people considered more. Square is too easy. Triangle is done. Then what is the next? Polygon. Square, triangle, and then rectangle, and then what is the next polygon? Pentagon, right? So people consider this kind of stacking. So initially 1 point, right? So it's like this. It is 1, right? And this is 1 point already counted, and then 4 more points, right? Do you follow me? Then this is 1 point counted, 4 more points counted, and then how many more points? 1, 2, 3, 4, 5, 6, 7 more points, right? 4 plus 7 plus what is your guess? 10, right? So let's verify. So people sometimes guess, and then using sometimes napkins, they just really check. So using your napkin or something, you can check. The next step requires 10. So this is the length 2, length 3. So length 3, I will make the frame first. Length 3, 3 here, 3 in this direction, 3 in this direction, and then 3 in this direction, and then 3 in this direction. So I made a frame, and then I plot on. So I plot these things, right? So do you follow me? Then let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. So we now have the idea. So this kind of idea is very important, right? Instead of just guessing and guessing, we can find a pattern. As you can see, we have like arithmetic progression. We increase the number, each number by 3 each time, right? Then once we know the sum of these kind of numbers, we can find the result. And people calculate it and then got the conclusion like this. The conclusion is this: n, 3n minus 1 over 2. Then let's review. I want to check whether you reviewed or not. I covered something on Monday, and I want to check whether you really reviewed or not. So this is the review. So first term is 1, right? Second term is 4. Then nth term. So this is the first term, second term. Then what is the nth term? Can you guess? First term is 1, second term is 4, and so on. What is the nth term? Can you guess? First term is 1, second term is 4. I will write more terms then. First term is 1, second term is 4, and the third term is 7, and then next term is 10. Then can you guess what is the nth term? Can you find the pattern? It is linear, right? It is line. It is line. So can you find the pattern? Slope is what? Each time? The rise over 1 is what? Right. Each time 3 is the increase, so automatically you can guess, oh, 3n is the, right? This is slope, right? Then can you determine the intercept, y-intercept? When n equals 1, what number did you get? 1, right? So how can you get that kind of number? 2, right? This is the generic. Please check whether you follow this or not. So we can find the first term, second term, and so on. And then by using these things, we can find nth term. Nth term is this one. Then let's add all these numbers. Let's add all these numbers. Then my conclusion is this: it is n, 3n minus 1 over 2. Then the challenge is this one. Prove that this is true. Then what should we do? If you are asked to prove it, what should you do? Induction. That's the tool. and then we add one next term. Then what is the next term? We replace this by k plus 1, right? K plus 1. So we add this term. 3k plus 1 minus 2 is added. And then this term plus the same term, right? 3k, and then this is 3 minus 2 plus 1, right? 3k plus 1. And the left side is 1 plus 4 plus all the way up to 3k minus 2, right? This is k, 3k minus 1 over 2. So I already assumed this for k. Do you follow me? And then because of this assumption, I just added this thing, then it is true, right? Then now, the left side it can be easily handled, so let's handle the right side. The right hand side now equals this thing and this thing together. So let's multiply this out. Then 3k squared minus k over 2, right? Over 2, right? So I multiplied out plus 3k plus 1. I multiply this out and then added 3k plus 1. Then I can simplify. 1/2 is the common factor. 3k squared. And then this is 3k minus 1/2 k, right? 3k minus 1/2 k. So 5/2 k, right? So 5/2 k, 5/2 k. And then this is 1 multiplied by this number. So it is 2. 2 over 2 is 1. I got this result. Then if we factor this, of course we don't cover factoring technique here. We just use factoring. If we factor this, 3k plus 2 multiplied by k plus 1. Then I want to write it in the pattern given in the formula. Then I will switch the terms. K plus 1 comes first, and then denominator goes down, and then this is rewritten 3 times k plus 1 minus 1. So what is this? It is nothing but the 1 with n equal to k plus 1, right? N equal to k plus 1. So we are done. So as you can see, even pentagonal number case is not very tough. In the past, when people didn't have these kind of tools, it was tough. Do you know what I mean? In the past, they didn't have these kind of symbols. They didn't have these kind of symbols. They know how to count on their own way, and as you know, Roman numeral doesn't look very systematic, right? So with those things, they should consider this, and then it was tough. But now we have all the tools such as nice symbols, equalities, and so on. So it is way easier to handle. But in the past, people considered these kind of numbers to handle some problems. I completed a proof using induction. So I showed you what kind of things people considered before. And I showed you how modern mathematics handle these kind of things very easily. Now we will jump to the division algorithm, which is the core of this course. Believe it or not, this is the core. Division algorithm, repeated, is Euclidean algorithm, and then these things are used to solve Diophantine equation, linear case, and so on. So this is the core. But if you have a question about early age problems, then ask. Then let's go to the division algorithm. Division algorithm sounds scary, but it is used from the elementary school time, right? Assume that your teacher asks you to divide 7 by 3. What do? You divide 7 by 3, then the quotient is what? 2. Then multiply this and then subtract, then the remainder is 1. So let's focus on these things. Quotient is 2, and the remainder is 1. And then these two numbers, 7, 3, are given by the teacher, right? 7, 3 are given by the teacher. So let's write it in equation form instead of this calculation form. 7 and 3 are given by the teacher, right? Then all you need to find is the quotient and the remainder. These are required, right? So this is the division algorithm. If you have two numbers, and if you divide one number by the other, then you have a quotient and the divide and the remainder. This is it. So in general, assume that you have two numbers A and B. So you have two numbers A and B. Then if you divide A by B, then the quotient and the remainder, right? And the remainder. This is the division algorithm. So if you hear the name, it is scary, right? If you look at the result, it is not very scary. Then why do we need it? As I showed you, this is the, if we repeat it, then it becomes Euclidean algorithm. And if we modify, then it is the technique to solve problems like this Diophantine equation. So very, very crucial. This simple thing is very crucial. So instead of proving this itself, right, proving this theorem itself, let's consider the application first. And then whenever we have time, we return back and prove it. Why? Because if I ask you to prove this on exams, you may waste about an hour to solve just one problem, right? So I don't want to ask this proof itself on the exam. Then where do we use the proof? Not very much, right? So I want to skip the proof and then try to use this theorem. So assume that you are asked to prove something in number theory. Then assume that you have divisor like 4. In other words, some number is divided by 4. Then, but because of the division algorithm, your number is 4 multiplied by quotient k. And then the remainder could be 0, right? And then, or this number, and then remainder could be what? 1. And then divide by this, and the remainder could be 2. And divide by this, and the remainder could be 3. If the remainder is 4, then we can divide it one more time to create bigger quotient, right? So this is it. So this is the application. So whenever you are asked to prove something, then use this. Then I will show you. I already mentioned that triangular numbers are there, and triangular numbers has this pattern. Has this pattern, right? The next task is this one. Prove this is an integer. Prove. We wrote down the triangular number and we said this is a generic term. So this is obvious. You can wave hand and it is obvious. It's triangular number, so it's integer. No, that's not enough. We want the proof. Do you understand what I mean? In other words, it's not hand waving course. Or just insisting that it's an integer. You should prove it. Then why is the clue? Division algorithm is the clue. So I will show you the full proof of this thing. So prove that, the question is prove that this is an integer, right? So you cannot just insist or say triangular number or all sorts of things. No. You need to prove it using what? Division algorithm. This is the key. When I first introduced you to this division algorithm, it looked very innocent and simple, right? It looked very simple. But it is so powerful to prove this kind of thing. The answer is yes. It's so powerful. Let's do it. If n equals, here divisor is what? 2, so n equals 2 times k plus 0. Or the next case, if n equals 2k plus 1, can you have remainder 2 or not? Not, because if you have 2, then you have bigger quotient and then remainder is. This is it. So there are two possible cases that we need to consider by the division algorithm. Someone may challenge you. Why? Then you can say, because of the division algorithm. Right? If you divide n by 2, then there is a quotient and the remainder is between 0 and divisor minus 1, right? Divisor minus 1. So I will write down the rigorous version after seeing these kind of thing, results or applications or usage. Then if this is the case, what happens? This can be rewritten 2k, then 2k plus 1 over 2, then 2 and 2 are cancelled out, and then k, 2k plus 1. Here k is an integer quotient, right? So k is an integer multiplied by another integer is an integer, right? So it's an integer. Do you follow me or not? Prove the second case. Prove the second case on your own. Done, right? So I divide, so key idea is this, very important. In the future, when you are asked to prove this kind of thing, you should remember the key idea. Key idea is this, we divide n, right? Divide n by 2, right? This is that. Because of the denominator 2, right? We divide n by 2. Then by the division algorithm, n equals 2 multiplied by quotient plus the remainder. And the remainder is nothing but some numbers between 0 and the divisor, right? Exclusive divisor, right? You don't include the divisor itself. I completely showed you on the usage. And one more example. It will not hurt. So I will pick something from the induction example. And induction example has this thing. So my question is this, prove that this is an integer. Prove that this is an integer. Then what is the number and what is the divisor? N is the number, right? Right? N is the number. And we divide n by what? 3. Then, what are the possible cases? Remainder equal to 0, 1, or 2. Do we have other cases? So, we should use this. So, I will show you first case and leave the other cases as your practice problems. Right? And in this case, plus 1, 3k plus 2, over 3. And then you can cancel out 3. So integer multiplied by integer and integer, so this is an integer. Done, right? then what are the cases you need to cover? If n divided by 3 happen to have remainder equal to what? 1 or 2. So you should use division algorithm to prove it. So division algorithm is the clue. Division algorithm is a clue. And there are many things like this, and I don't want to spend too much time on these things, but if you are interested in many other things, you can ask me. Then before going further, I will describe the division algorithm in full theoretical form. Instead of just giving you an example, I will describe the division algorithm in very, very rigorous form. But it cannot be very difficult. But if you have a question, ask up to this point. So division algorithm, instead of writing down, I will type the division algorithm. So this is the rigorous form of the division algorithm, yeah? Sorry, you are right. Thank you. So this is the rigorous description. It's not very different from the earlier version that I gave you. And one more thing that I need to attach is this one. I didn't complete the description, so I'll delete it and then complete the description. And we call this quotient. It's not very good to use this thing, so I will remove this thing and then use different color. I don't understand what happened to software. Oh, line color, sorry, I chose wrong. It was my mistake. So do you follow me? And of course, you know everything, right? This is called what? Divisor And this is called what? So in my opinion, you heard these things when you are an elementary school student, right? So we use these things to prove many things. In addition to proving many things, we apply these things in Euclidean algorithm. We apply these things to solve Diophantine equation. In any case, I showed you many cases. Then the next thing that I want to consider is this one, divisibility. So I will write the definition of divisibility. We say definition, and we say A divides B, or the same thing, B is divided by A, right? And then in notation form, we write it this way: A divides B. It is the vertical bar. A divides B. So these are all definitions. If there is an integer x, satisfying this, right? If there is an integer. X satisfying this. Do you follow me? In other words, in the division algorithm, if the remainder is 0, right? If the remainder is 0, then it is called A divided B, right? Very trivial fact. Only thing that might be non-trivial is the notation, right? Introduction of the notation. A divides B. So when I write this thing, you should, this in your mind, right? You should have this in your mind. Do you follow me? So when I write A divides B, it means B equals A times X. Is X absolute thing or just generic thing? It's generic, so you can replace this X by any letter, right? Any letter. So this is the definition, and using this thing, we can create many, many things. So text used the C instead of X. I used X, text used C. Doesn't matter, because as I mentioned, it's generic. And the next thing is this one. If not, then what would be the notation? A does not divide B. So we just strike out, right? A does not divide B, right? In other words, if B is not equal to AX, then it is this. Then this has some properties, some tedious properties. But before mentioning about tedious properties, I will write down possible alternative way of describing this divisibility. I said A divides B, or B is divided by A, but there are many other ways of describing the same thing. So I'm just introducing a few cases using text examples by typing, right? I will type them, and you will see. So this is one expression, right? Obvious, right? Another expression, right? Right? So I just gave a few ways of describing this divisibility. Do you follow me? So there are, because I chose wrong background, I'm paying for it. It should be white, right? So a little bit dim, right? But in any case, the same thing can be described differently, right? It's not very difficult. In any case, I will mention about very tedious properties, but all the time, what you need to remember is this conversion. When you see this thing, what should you have in your mind? What should you have in your mind? This one, right? So when you are asked to prove or disprove, then you should have this thing in your mind, and I will begin to write down the properties. First property, A divides 0. A divides 0. Then you need to prove it. What should you do? So you should say, what? 0 equals A times something, right? 0 equals A times what? 0. So 0 equals A times 0. So proof is done, right? Proof is done. Thus, we can say this, right? So 0 equals A multiplied by 0. This is a fact, right? This is a fact. So because I established the equality statement, I can say this, right? Once I establish this statement, I can always return back to this equivalent thing. You follow me? Next thing. Next thing is this one. We can say 1 divides number. Here A, B, C, all these are integers. All of these are integers. 1 divides A. Then what is the proof? Can you write the proof? One line proof. Proof is what? A equals what? 1. Right? A divided by 1 is what? A. Done, right? So we can conclude. Proof is done. So all you need to do is establishing this, right? The next thing, A divides A. What is the proof? If you divide A by A, what is it? So you say that 1 is multiplied, right? So because of this establishment, I proved. Then the second property. So the first property is very trivial or straightforward. Second property is this one. If A divides 1, if and only if A is either plus 1 or minus 1. So A divides 1 if A is equal to plus 1 or minus 1. So the other direction is easier. So I will prove this direction first. Proof of this direction, right? Proof of this direction. So this direction is easier. So assume that A equals this one. If A equals this one, I don't want to write full statement, just describing might be enough. Plus 1, plus minus 1 is A, right? So A is divided by 1. A is given then. If you divide this by 1, then what will be the quotient? What will be the quotient? If you divide this by 1, what will be the quotient? Quotient will be this thing, right? Done. Because I established this kind of relation, plus minus 1 is divided by 1. Do you follow me or not? So once I establish this thing, I conclude that 1 divides plus minus 1, which happen to be A, right? So done. So the other direction is easier. Now the next thing. This direction. A divides 1 can be written this way. 1 divided by A, right? Do you follow me? 1 divided by A has quotient or some number, right? Do you follow me or not? So there is an integer q satisfying this. There is an integer satisfying this. Of course, because product is 2, neither q nor a is 0, right? Neither q nor a is 0. Do you follow me? These are all integers, but non-zero integers. Then what is the next integer? Possible smallest integer. Plus 1, minus 1, right? So, q, neither q, right? Neither q nor a is 0. And both are integers, right? And both are integers. If q or a are greater than q absolute value and a absolute value are greater than 1, then q times a absolute value is also greater than or equal to a, right? Not equal to, but greater than 1. Do you follow me or not? If you don't follow me, I will slow down. As I mentioned before, this is a little bit tougher because we need to describe the situation logically. But, right? Thus, q absolute value and then a absolute value should be 1, right? Because it is not 0. It cannot be greater than 1. It's an integer. Then what are the numbers? 1, right? Do you follow me or not? Thus, a should be, because of this fact, a should be equal to plus minus 1. Done. I completely proved it. If you doubt or have a question, ask me. If you don't, I will continue. Yes?
We need to show also that q is plus or minus 1? Or
doesn't matter. Q, yeah, Q is an integer, right? So all we want to focus on is A, right? A is. So please browse and check what step look difficult. Take a look. This is straightforward conversion of this language, right? We convert this into this language, right? This bar, right? This whole vertical bar is converted to equal conclusion is AC divides BD. is look or sound very complicated, but in reality, this is easier than the previous one. Because just by routine conversion, we can prove it. So let's do it. I want to change the language from vertical bar language into equality language. Then what is it? What is it? Right, B equals QA or Q1A, right? And then if we convert this thing, then D equals what? CQ2, right? You translate it. So what is it? First statement should be what? If we translate, B equals A multiplied by Q1. And then if we translate this, C equals B multiplied by Q2. I translate it. Then the next thing I need to do is rewriting it. Then, because of the previous fact, B is what? This B is what? AQ1. Then it is, what did I do? Why do I have C? Then A times Q1, Q2. Then this is the conclusion, right? Once we have this, we convert this to bar language, right? Bar language. So between bar language and equality. Who do you around here? Q1 should be equal to plus minus 1, and at the same time Q2 should be equal to plus minus 1. Do you follow me? The same reasoning. Q1 divides 1, right? Q1 divides 1. If we translate this, Q1 divides 1, right? Or Q2 divides 1. Then, as I showed you before, do I have it right here, right? Because of this. Here, take a look. If Q1 divides 1, then Q1 divides 1, then Q1 should be plus minus 1. Do you follow me? So I'm using this back. So this is the same as, this equation language is the same as saying this one, right? Then by the first property that I proved, Q1 should be plus minus 1. Because Q1 should be plus minus 1, we can get this conclusion. Or Q2 should be plus minus 1, we can get this conclusion. Either way is possible. Because of this, A equals B times this one, right? Plus minus 1 or plus minus B. Done, right? The other way is trivial. So what I showed you is this direction. I showed you this direction proof, right? This direction. I will show you the other way. But if you do not understand, then ask me. This is the mathematical symbol people use. This means this step is done, right? This means this step is done. Then the next thing is the other way. So what about the other way? Assume that A equals plus minus B. Then what can you say? Oh, B equals A multiplied by what? B equals A multiplied by what? Plus minus 1, right? And then A equals B multiplied by what? Plus minus 1. So I found the quotient. Do you follow me? So because of this reason, if I translate this, then what is the conclusion? The top conclusion is what? A divides B, and then this B divides A. That's all we wanted, right? This is all we wanted. Done. So proving is translating in this portion, right? In this portion, proving is nothing but translating and do very simple, straightforward calculation of equalities. The next thing, F So let's do it. because it is not 0. So the same thing over and over again, right? The same idea over and over. So what is it? I've completed the proof. What did we want? We wanted to prove that B is less than A, right? But in reality, trivial fact, if A divides B and A divides C, then A divides B times any number, and then C times any number. This is the conclusion. Do you follow me? So if A divides, I will rewrite A. It doesn't look good. I will rewrite A here. So if A divides B and C,